Now, in the next part of this section, we'll work with determining a basis for the null space or the column space of a matrix A. So what we've already taken a look at in section 4.2 is how to find a set of vectors which span the null space of a matrix A. So recall in our last section, when we were finding an explicit description of the null space of a matrix, we were finding a collection of non-zero vectors which span that null space. And the column space of a matrix, by definition, is a spanning set of the columns of that matrix. Now, when we talk about the null space, recall that that method of finding a set of vectors which span our null space will always produce linearly independent vectors if the null space of A contains non-zero vectors. Therefore, this method that we were looking at in section 4.2 of finding a spanning set for the null space produces a basis for the null space, because the vectors which we find are guaranteed to be linearly independent. So finding a spanning set for a null space using the method of section 4.2 is equivalent to finding a basis for our null space. So let's look at an example of this. In this first problem, we're given a 3 by 5 matrix A, and we are asked to find a basis for the null space of that matrix. So recall, the null space of a matrix is the set of all vectors x, which are mapped by the matrix A onto the 0 vector. So in order to solve this homogeneous equation or a homogeneous linear system, we could consider an augmented matrix. So let's take the matrix A, whose first row was 1, 0, -5, 1, 4. Second row was -2, 1, 6, -2, -2. And third row was 0, 2, -8, 1, 9. And augment that with the 0 vector, since this is a homogeneous linear system. And we want to perform row reduction on this to reduce it to a reduced row echelon form. So in our first row, we already have a leading coefficient of 1, which I'm going to use to eliminate the -2, which appears in the row below that. Now to accomplish that, I can take row 2 and add twice row 1. So my first row will remain 1, 0, -5, 1, 4, 0. And my second row, I'm going to leave alone, or excuse me, my third row, I'm going to leave alone in this step. And performing this operation, my second row becomes 0, 1, -4, 0, and let's see, 8 minus 2 is 6, and 0 plus 0 is 0. So now I have a leading 1 in my first row with zeros below it. I have a leading 1 in my second row with a 0 above it, and I'm going to use that 1 to kill off the 2 that appears in the third row by taking row 3 minus 2 times row 2. So my first row remains 1, 0, -5, 1, 4, 0. My second row will be the same, 1, 0, 1, -4, 0, 6, 0. And performing this operation, my third row becomes 0, -2 plus 2 is 0. We have 8 minus 8 is 0. 0 plus 1 is 1. and then negative 12 plus 9 leaves us negative 3 and 0. So now I have a 1 as the leading entry for my first and second row, with zeros everywhere else in those columns. And in my third row, I have a leading entry of 1 with a 0 above it, and then I still need to kill off this 1 that appears in the first row, fourth column. So to accomplish that, I'm going to take row 1 and subtract row 3. So my first row becomes 1, 0, negative 5, 0, 7, 0. And then my second row, I'm leaving alone. Same with my third row. So we now have a matrix which is in reduced row echelon form. We see that it has pivot columns as the first, second, and fourth column. So the third and fifth column will correspond to free variables. So our solution set for this equation, which will give us a description of the null space, is the set of vectors x in R5, where our first component, x1, is equal to 5x3 minus 7x5, using row 1 of this matrix. X2 is given by 4x3 minus 6x5, using the second row of our matrix. X3 is a free variable. X4, using the third row of my matrix, is equal to 3 times x5, and x5 is a free variable. If we write this as a linear combination of vectors where our weights are the free variables, we could write this as x3 times the vector 5, 4, 1, 0, 0, plus x5 times the vector negative 7, negative 6, 0, 3, 1. All right, so these two vectors span the null space of this matrix A, the set of all vectors x which can be written in this form. And we can see clearly by examination of these vectors that these are linearly independent. Also, this process generates a set of linearly independent vectors because if one could be written as a linear combination of the other, then there would be one less free variable. These two vectors, let's maybe call them v1 and v2, form a basis for the null space of A. So here, the basis that we're interested in, B, would be the set of vectors v1, v2, which we found here. All right. So our same process that we were using in section 4.2 to find a spanning set for a null space is guaranteed to generate linearly independent vectors which span the null space and therefore a basis for our null space. So let's consider the problem of finding a basis for the column space of some matrix. So the following examples, the next two that we're going to consider, will describe a sort of algorithm for finding a basis for such a column space. So in our first example, let's consider finding a basis for the column space of B, where B is the matrix whose columns are the vectors B1, B2, up through B5, shown here. And by examining the columns of this matrix, we can see that some of these columns can be written as linear combinations of the others. So in particular, each non-pivot column of the matrix B is a linear combination of the pivot columns. So for example, for this matrix, column 2, that is the vector B2, is equal to 4 times B1. We see that to get the second column, we just take our first column and multiply by 4. Now what else are our pivot columns? So here we had pivot columns given by the first, third, and fifth columns. So B2 and B4 were non-pivots. We've seen that B2 is 4 times B1. And for our fourth column, B4, we can write B4 as 2 times B1 to get a 2 as that first entry. And then to get a -1 in the second entry, I could subtract 1 times B3, my third pivot column. So, by the spanning set theorem, I have a set of vectors, namely the column vectors of B, B1 through B5, which span the column space of B by definition, but 2 of those vectors can be written as linear combinations of the others. Now, the spanning set theorem said that we can then discard those vectors, which are a linear combination of the others. So here we'll say we can discard the vectors B2 and B4. So the column space of B, which was the span of B1 through B5, is equivalent to the span of the vectors B1, B3, and B5. Now, we can see pretty clearly by examining B1, B3, and B5 that they are linearly independent. So in particular, if you look at these 3 columns, here, here, and here, we can see that none of them are scalar multiples of one another. Therefore, or let's say since, none of the vectors B1, B3, and B5 are a linear combination of the others. The set B1, B3, B5 is linearly independent. So this set of vectors, B1, B2, B1, B3, B5, spans the column space of B by definition. And we've shown that this set of vectors is also linearly independent, because clearly no one of them is a multiple of the other 2, or a combination of the other 2. Therefore, that set forms a basis for the column space of B. So here, B, or you'll notice in the book we use sort of this script B instead of a regular B for a matrix to denote a basis. which would be the set of vectors B1, B3, and B5, which forms or is a basis for the column space of B. So we see here that this example gives us sort of an outline for how to find the basis for the column space of a matrix. Now in that first example, the matrix B that we were given was in row echelon form, in particular reduced row echelon form. We could write any of the non-pivot columns as a linear combination of the others. So let's consider a matrix which is not in reduced row echelon form. So what about such a matrix A, which is not in reduced row echelon form? Well, we can recall that any linear dependence relation among the columns of a matrix A can be expressed in the form A times X equals 0, where X would be a vector whose columns are the weights of that linear dependence relation. And if we take a matrix A and we row reduce it to a matrix B, then the columns of B may be different from the columns of A. However, the equations AX equal to 0 and BX equal to 0 have the same solution set. We said that by performing row reduction on a matrix, it does not change the solution set. We get a system which is identical to the solution set of our original system. That is, the columns of A would have exactly the same linear dependence relation as the columns of B. Therefore, if we have a matrix A which is not already in reduced row echelon form, we can perform row reduction on it to put it in reduced row echelon form, and then use the same sort of process that we did in our last example in order to find a basis for that column space. So let's look at an example of this. It can be verified, we won't go through the work of it here, that the matrix A can be reduced through row operations to the matrix B, and we are asked to then find bases for the null space and the column space of A. All right, so let's see if we can determine, first off, a basis for the null space. So in order to find a basis for our null space, we would consider the equation A times X equals to 0, which has the same solution set as B times X is equal to 0. And we want to describe these vectors B, or X, that would solve this. So looking at our matrix B, it has been written already in row echelon form, and through rewriting this in reduced row echelon form, we can come up with our solution set. So here, let's consider our augmented matrix for this system, where we have the matrix B, 1, 2, 0, 4, 5, 0, 0, 5, negative 7, 8, 0, 0, 0, 0, 9, and a row of all zeros. So augmenting that with the 0 vector, if we perform row reduction on this a little bit, we can see that, well, we have a 1 as our lead entry in the first row, zeros below it. Our lead entry in the second row is a 5, and we have zeros above and below it. We just want to make that lead coefficient a 1. And in the third row, our lead coefficient is a 9, which we want to be a 1. So if we perform row reduction on this matrix, I could start by taking 1/9 of my third row, which makes my third row 0, 0, 0, 0, 1, 0. My fourth row consists of all zeros, so I'll leave it alone. Now, my first row already has the appropriate form. I'm going to leave it alone. And let me multiply my second row through by 1/5 so that that lead coefficient will become a 1. So I'll take 1/5 of row 2 to get 0, 0, 1, -7/5, 8/5, and 0. So now I have leading entries of 1 in each of these rows, but I need to eliminate the 5 and 8/5 that appear above the leading 1 in my third row. Now I can easily do that by taking row 1 minus 5 times row 3, or row 2 minus 8/5 times row 3. So performing those indicated operations, we're left with the matrix 1, 2, 0, 4, 0, 0, 0, 0, 1, -7/5, 0, 0, 0, 0, 0, 0, 1, 0, and a row of all zeros. All right. So this matrix B in reduced row echelon form has pivot columns as its first, third, and fifth columns. So let's see if we can describe our solution set. So the solution set would be the set of vectors x such that, so these are vectors in R5, where our first component, x1, using the first row of our matrix here, is -2x2 minus 4 times x4. x2 is a free variable. x3, using the second row of our matrix, is equal to 7/5 times x4. x4 is a free variable. And using the third row of our augmented matrix, x5 is 0. So if we rewrite this, we can express this as the free variable x2 times -2, 1, 0, 0, 0, plus the free variable x4 times -4, 0, 7/5, 1, 0. So these two vectors are a linearly independent spanning set of the set of vectors x of this form, which defines the null space of the matrix A. So if we call these vectors maybe v1 and v2, then a basis for the null space would be the space B, consisting of these vectors v1 and v2, is a basis for our null space. Now, second part of this example asks for a basis for the column space, and so we see from the form of B, as we did in our last example, that the non-pivot columns, those are columns 2 and 4, can be written as a linear combination of the pivot columns. So in particular, for this example, we can say that B2, our second column vector, is equal to 2 times B1, and B4 is equal to 4 B1 minus 7/5 B3. All right. So these linear dependence relations among the columns of B must also be true for the columns of A. So A2 is equal to 2 times A1, and A4 is equal to 4A1 minus 7/5 A3, where A1 through A5 are the column vectors of the matrix A. So we see by the spanning set theorem that since A2 and A4 can be written as a linear combination of the other vectors, we can discard those two vectors when we're selecting a minimal spanning set of the column space. So, as with our last example, by the spanning set theorem, we can discard the vectors A2 and A4 when selecting a spanning set for the column space of A. So here, our column space of A, let's see if I can squeeze this in, is the span of the vectors A1 through A5, the columns of A, but we saw that we could discard A2 and A4, so this is the span of A1, A3, and A5. All right. Now, we have a spanning set of vectors for the column space. We just need to show that they are linearly independent in order to show that they form a basis. However, these three vectors, A1, A3, and A5, must be linearly independent, because if there were a linear dependence relation among these three vectors, then there would have been the same linear dependence relation among the column vectors of B. And we've already established all of the linear dependence relations among the columns of B. So we can say also here, the set of vectors A1, A3, and A5 are linearly independent. So the set of vectors B, consisting of the first column, third column, and fifth column of A, are a basis for the column space of A. All right, running out of room here. This example shows how we could find the basis for a null space of a matrix, or by row reduction of a matrix, we could find a spanning set or a basis for the column space of that matrix. So these last two examples can be generalized to establish the following theorem, 4.6, which say that the pivot columns of a matrix A form a basis for the column space of A. Because If A can be row reduced to some matrix B, which only has so many pivot columns, well, all of our non-pivot columns are linear combinations of the pivot columns. Therefore, the original matrix A has non-pivot columns, which are a linear combination of its pivot columns. And then by applying the spanning set theorem, we see that a basis for the column space of A would then be the set of pivot columns for our matrix A. All right. So generally, in order to determine the basis for a column space of a matrix, we just need to identify the the pivot columns for that matrix. So making use of this theorem, let's look at another example. So here we are asked to find a basis for the space spanned by the 5 given vectors here. So in order to find a basis for that set spanned by these vectors, let's introduce a little terminology. So here, let's let H be the space spanned by V1 through V5. Now, we can think about this set H as, I'll write it up here to save a little space. We'll say that our set H is equivalent to the column space of a matrix A, where A is the matrix which has these vectors as its columns. 1, 0, 0, 1. -2, 1, -1, 1, 6, -1, 2, -1, 5, -3, 3, -4, and 0, 3, -1, 1. Now, as we've seen in Theorem 4.6, to find a basis for this column space of our matrix, which is the space A spanned by our vectors, we just need to identify the pivot columns of this matrix, which means that we need to reduce this matrix to row echelon form. It does not need to be reduced row echelon form, since we're just looking for which columns are pivot columns. So here, in our first step, we could reduce this by taking row 4 minus row 1. So my first row will remain as 1, -2, 6, 5, 0. My second row will be 0, 1, -1, -3, 3. If I perform this operation on my fourth row, I would have 0, 3, -7, -9, and 1. So let's see. Then in my third row, I see if I add the second row to it, I can simplify a bit further. So I might take row 3 plus row 2, which would give me 0, 0, 1, 0, 2. So now my matrix has a leading entry in the first row of 1 with zeros below it. I've got a leading entry of 1 for my second row, which I'm going to use to eliminate the 3 that appears below that in my fourth row. So that is, I'm going to take row 4 and subtract 3 times row 2. So my first row is 1, -2, 6, 5, 0. I'll have a second row, 0, 1, -1, -3, 3. A third row of 0, 0, 1, 0, 2. And performing this operation, my fourth row becomes 0, 0. I've got 3 minus 7 is negative 4. Then let's see, 9 minus 9 is 0, and negative 9 plus 1 would be negative 8. So we then have the matrix almost in row echelon form. There's one more step that we need to perform. So using the leading 1 in my third row, I can kill off the negative 4 that appears in that last row by taking row 4 and adding 4 times row 3. So I have 1, negative 2, 6, 5, 0, 0, 1, negative 1, negative 3, 3, 0, 0, 1, 0, 2, and 0, 0, 0, 0, 0, a row of all zeros. So I see for this matrix in reduced row echelon form that the first, second, and third columns are my pivot columns, and columns 4 and 5 are non-pivots. So by applying theorem 4.6, I find that a basis for the space H, which was the column space of this matrix A, would be the set B of column vectors of the first 3 column vectors of A. Those are the pivot columns of the matrix A, which were, if we write these out, 1, 0, 0, 1, negative 2, 1, negative 1, 1, and V3, which was 6, negative 1, 2, negative 1, or equivalently, the vectors V1, V2, and V3. They form a basis or a minimal spanning set for the set H of vectors spanned by V1 through V5. Okay. So in the last part of this section, we'll consider 2 different views of a basis. So one way to think about a basis is the following. If we're applying the spanning set theorem, then the deletion of vectors from a spanning set must stop when that set becomes linearly independent. If we were to delete additional vectors, then our set would not be a linear combination of the remaining vectors, and therefore the smaller set will no longer span all of V. So we've deleted some vector which is needed to span the complete vector space V. So we can think about a basis as a spanning set that is as small as possible. Now, another view of a basis is the following. Another way to think about a basis is as a linearly independent set, which is as large as possible. So if S is a basis for a vector space, and if S is enlarged by a single vector, let's say W, from our vector space, then the new set cannot be linearly independent because the set S already spans V, and W, which is an element of V, is therefore within the span of S and a linear combination of the elements of S. So we can also think about a basis as being a linearly independent set which is as large as possible. So in our last example, we'll illustrate a few sets in R3, which show how a linearly independent set could be enlarged to find a basis, but how further enlargement by adding additional vectors would destroy the linear independence of that set. And this also illustrates how a spanning set could be shrunk down to a basis, but further shrinking by deleting a vector would destroy the spanning property. So in part A of this example, we are asked to show that the set consisting of these two vectors is linearly independent, but does not span R3. So here we can say, maybe if we give these vectors names, let's say v1 and v2, we can say that clearly the vectors v1 and v2 are linearly independent, since they are not multiples of one another. Remember, a set of two vectors is linearly dependent if and only if one is a scalar multiple of the other. So these are clearly linearly independent. However, as we mentioned in an earlier example from this section, a set of only two vectors cannot span all of R3, since the number of vectors is less than the dimension of our space. We've established what we desired. Another way we could show that these two vectors do not span all of R3 is again to put these in the columns of a matrix A, and we see here A is already in row echelon form. It has a row of all zeros as our last row, therefore any vector in R3 whose last entry is non-zero cannot be a span of, or cannot be a linear combination of these two vectors. So in part B, let's suppose that we have the following set where we take the same two vectors v1 and v2 and we add a third vector v3. So we want to show that this set forms a basis for R3. So similar to an example that we considered earlier in this section, an easy way to show that this is a basis is to consider a matrix A, which has these vectors as its columns, and show that this is invertible. Now we can see that this particular matrix A is upper triangular. So recall from chapter 3 that the determinant of a triangular matrix is the product of its diagonal entries. In this case, 18. So since we have a non-zero determinant, A is invertible. And by the invertible matrix theorem, that means that the columns of A, which are these three vectors, form a linearly independent spanning set of R3 and are therefore a basis. So here, our set of vectors v1, v2, v3 is a basis for R3. So comparing this to part A, by adding one additional linearly independent vector, we now have a basis where we did not have that in part A with the set of only two vectors. Now in part C, we are considering a set of vectors v1, v2, and v3 as with part B, and then we add a fourth vector v4, and we're supposed to show that this spans R3 but is not linearly dependent. Now we already know that the first three vectors span all of R3 by part B. So by part B, we know this set spans R3, since the first three vectors alone spanned all of R3. However, this set is not linearly independent because we have four vectors of dimension 3. So recall from chapter 1, we had a result where if you have more vectors than the dimension of those vectors, they cannot be linearly independent. So let's say, however, a set of four vectors in R3 cannot be linearly independent by using that result we had seen in chapter 1, which is theorem 1.8. So if we take a basis and we add an additional vector, we get something which cannot be linearly independent, and therefore no longer is a basis. So by adding additional vectors to a basis, we lose out on the linearly independent property. Or if we took the basis from part B and we deleted a vector to get to the set we were considering in part A of this example, we saw that we still have linearly independent vectors, but we lose that spanning property. So comparing these sets of vectors in parts A, B, and C illustrates these two different ways to view a basis, either as the smallest possible spanning set or the largest possible linearly independent